So a couple class periods ago, we talked about solving problems with trig, but one thing you may have not realized was happening with all of these triangles is that all of them sort of looked the same. What do you think I mean by that? They were all right triangles. Now, in real life, how many times are we going to get a perfect right triangle? Hardly ever. So what we're going to do today is leave these problems alone for a second where you have nice, pretty right triangles, because those are the easy problems. Because we already know one of the angles is 90 degrees. It allows us to do trig a lot faster because we're not having to solve for all of the angles, usually just one of them. Today, since we are leaving these right triangles, we're going to get into a couple laws of triangles. The first law of triangles today is called the law of cosines. It's our first step. It's the first thing we use to solve non-right triangles, which is just a general term for literally anything other than a right triangle. So your equilateral triangles, your isosceles triangles that are not right angles, all of those are the ones we're going to be able to solve today. Sometimes the law of cosines is actually going to be called, and this is longer than this space is allowing you, it's called generalized, that's not how you spell that word, let me try again. Non-right triangles. Generalized Pythagorean theorem. Yeah, I know, I did not give you enough space for that on that little line there. Yeah, it's weird to abbreviate. Abbreviated theorem. But generalized Pythagorean theorem means that we're going to be able to apply the idea of a squared plus b squared equals c squared to triangles other than right triangles. Because the Pythagorean theorem only works when you had a right triangle. So if we use a generalized version, we're going to be able to do this theorem for more than just right triangles. But it's going to be called the law of cosines because generalized Pythagorean theorem is a mouthful. We call it law of cosines. Now, something we need to kind of establish for today is what the usual way to label a triangle is going to look like. So a lot of your problems are going to say the triangle has been drawn or labeled the usual way. So here's what the usual way looks like. If you have angle A here, the side length directly across from it is side length A. Now notice I used a capital A for the angle and a lowercase a for the side length. That's important. You have to know that difference. Then you have, if this is angle B, where is side length B? The opposite. Always the opposite of it. But it's not going to be opposite adjacent hypotenuse. There's no hypotenuse. There's no right angle. But if you always think of it as the opposite side of the angle, then we're good to go. That means this is going to be angle C, no longer a right angle. And the side length across from it, or the opposite side of it, is going to be side length C. Now here's an annoying thing about the English language and these letters. Capital C and lowercase c look the same. So if you want to, on your capital C, give it like a little flourish on the top so you know that it's not a lowercase letter, I would recommend that for yourself. Sure, however you want to indicate that you know that that's a capital C compared to the lowercase c. Mine are just generally bigger, but if your handwriting is not consistent on how big you write your capital and lowercase letters, make sure you know the difference because that's going to be important. So again, across from angle A is side length A, across from angle B is side length B, and across from angle C is side length C. So these are all opposites. So anytime that the problem says the triangle is drawn the normal way, you're going to draw your triangle like this. The formula for law of cosines has 3 versions depending on what you're trying to find. Now this is a huge formula for us today and for the next test you're going to have next week. I'm going to expect that you have this memorized, just telling you that right now. On that test I will give you some formulas. This is not one of them. I need you to have it memorized. Since there's 3 versions, it's like a lot of things to remember unless you start noticing the pattern. So the law of cosines, notice it all starts with Pythagorean theorem. If you have or want to find A, we know that A squared for non-right triangles will be B squared plus C squared minus 2B, I just used the wrong color. I'll get it together. 2BC times the cosine of angle A. So here's some things I notice. the side length I'm finding is the angle I'm using. Do y'all see that? Which means the other letters that are in the formula have to just be the other letters, B and C. So if I'm trying to find B, I'd have B squared equal to, I'm using angle B, and the other two letters are what is in the formula. A squared, C squared, minus 2 times AC. So in the third formula, if we're trying to find side length C, the angle that will be used in the formula is C, and the other two letters must be used in the other spots. So here's A squared, and here's B squared, minus 2AB. Which means you can kind of generalize this generalized Pythagorean theorem a little bit further and to say that you have the opposite side, whatever the opposite side length that you're looking for, squared, equal to an adjacent side to the angle squared plus an adjacent side to the angle squared minus 2 times that adjacent angle and the adjacent angle, all multiplied by cosine of the angle theta. So if you have a theta that you know and you want the opposite side length, but you know the other sides, we have a formula for it. Okay, again, I'm going to expect you have this memorized.
So opposite a
Theta, basically.
So everything is squared is plus, minus, then multiply.
Correct. Okay. So there's a proof for the law of cosines, and it's actually really interesting, but I know most of you guys don't find proofs interesting. A proof of a formula is basically like the explanation of why it works. I'm not going to go through it, but this is a great explanation of why we have this formula to begin with, starting from the distance formula, ending at the law of cosines. But we're not going to quite go over that because I know you don't really care. What you care about is being able to actually use it. Now, when we use the law of cosines, there's going to be two scenarios that we were going to use it. Those two scenarios are when you have a side angle side and when you have side side side. Do y'all remember what those things mean? If you are given a side of a triangle, then the angle, and then immediately the next side, we're going to be able to use the law of cosines. If you are given all three sides of a triangle and we're asked to solve for the rest of them, we're going to be able to use the law of cosines.
So is this one SSA?
This one is, that is a big C. So so first of all, let's draw our triangle in the usual way. It's going to be really helpful every time we do this. So here's a side length, and here's a side length. Try not to make it look like a 90-degree angle because you'll confuse yourself. It is not a 90-degree angle. And we label it. Here's angle A, side length A, right across from it. Angle B, side length B. Angle C, side length C. This is the usual way. So every time you have a triangle that we're doing these sorts of problems with, you want to make sure you draw it. Indicate no 90-degree angle or no more right angles. And then we label what we know. Well, we know that angle C is 20 degrees, so I'm going to add 20 degrees in there. I know that side length A is 11 units, and I know that side length B is 5 units. So if we were trying to solve this triangle, what three things are we trying to find?
We're trying the angle of A, the side length of C, and the angle length.
Yeah. Angle of A, side length C, angle B. Those are the three things we need to find. Okay. We are given a side length, an angle, and a side length. For side, angle, side, we're going to be able to use the law of cosines. Yes?
Do they have to be connected?
The side, angle, and side?
Yeah.
Yes. Otherwise, it's a different congruence theorem.
Okay.
If it was like this side, this would be side, side, angle, and that's not congruent.
Oh, okay.
So you do need to make sure you remember those things from geometry. Side, angle, side is good.
Do you go clockwise in terms of like reading them?
Doesn't matter. Because it would be side, angle, side if I went the other way. And it would be angle, side, side if you went the other way, and that's not good. No. Either way. Okay. So the first thing we're going to do is we're going to try to find side length C using the law of cosines. So if we want to find side length C, then we're going to use the version of law of cosines that is solved for C squared. Meaning we're going to use c squared equal to a squared plus b squared minus 2 times a times b times the cosine of big C. I guess I should have put this in. Okay. Do we know side length A?
Yes.
Do we know side length B?
Yes.
Do we know angle C?
Yes.
Oh, snap, we know everything. Okay, so we just plug everything in. So C squared is going to be equal to 11 squared plus 5 squared minus 2 times 11 times 5 times the cosine of 20 degrees. Now, first of all, make sure your calculator's in degrees. And that is all numbers, which means that's something I can just throw into my calculator and call a day. Yeah, so we should have gotten, remember this, by the way, this is C squared. C squared is going to be equal to 42.63 units. Again, we're going to round to 2 decimals every single time, which means, since that's C squared, what is C? 6.53 units. Cool. All right, so we found side length C. That's one of the 3 things we needed to finish solving this triangle. What are some of the other things we needed?
Angle B.
Angle B. Sure, we can start with finding angle B. We could also start with finding angle A. And just because I have it written down on my paper with A, we're going to solve for A first. So if we want angle A, and we look back at the law of cosines that we have, which version of law of cosine uses angle A? So looking where it says the A's, B's, and C's inside the cosine stuff, that's the only angle we've used. Which one says A in there? The first one. And that first one was A squared equal to B squared plus C squared minus 2 times B times C, again, all the things but A, times the cosine of angle A. But here's the deal. For this problem, we want angle A, which means we actually would rather have a formula that says A equal. So we're going to derive a formula. That way you can have it on your notes and not have to derive a formula again. Derive means solve. We did this when we were practicing for SAT. We're going to rearrange the equation so that it says A equals, big A equals. Which means the first thing I need to do is move these 2 things away from the term that has the big A in it. How do I move B squared and C squared away? Yeah, subtract them. So this is actually going to be A squared minus B squared minus C squared equal to negative 2BC cosine of angle A. All right, one step closer. I'm still trying to get this angle A by itself. Right now, angle A is contained within cosine. So I first need to isolate cosine, then we'll deal with the cosine. So what do I need to get rid of on this term so that just cosine of A is there? Minus 2BC. Now, minus 2BC is currently multiplied by cosine, so what do I do to get rid of it? Divide. So then I'm going to have A squared minus B squared minus C squared divided by negative 2BC equal to the cosine of A. So we just divided by essentially the coefficient of cosine, which happens to be a letter and a number. 2 letters and a number. Ooh, we are so close to having A by itself. We need to get A out of the cosine function. What is the inverse of cosine? Arc cosine or inverse cosine, which means we can write a formula for angle A if it is the inverse cosine or arc cosine of A squared minus B squared minus C squared all over negative 2BC. Whew. After lunch, we'll actually do something with this. So now that we're back from lunch, let's remember what we have done so far. In this problem, we first needed to find side length C because we have a formula derived for side length C already given in law of cosines. Then we're like, okay, cool, got that. We need to find angle A and angle B. It does not really matter which one you do first. I like going in alphabetical order myself, so I went for A first. But since angle A is inside the entire function, I want to derive the formula for angle A. Now this right here is something I would like highlight, circle, star, underline, because this is the derived pattern for all of the derived versions. So anytime you want to find an angle, it's going to follow these patterns, where the angle is going to be equal to the inverse cosine of the opposite side length squared minus the adjacent squared minus the adjacent squared divided by -2 times the adjacent times the adjacent. So you can substitute in the different letters there depending on what you need. So I would put a bunch of stars next to this one because you're going to want to not have to do that work again and just use the derived version, which means this is probably something you want to memorize as well. This is the derived formula. But once we have a derived formula, we can just plug in what we know because the formula itself uses just the side lengths A, B, and C. Do we know the side lengths A, B, and C?
No A and B.
We were given A and B. Didn't we just find C, though?
Oh, yeah.
So we know it. Okay, we can plug everything in. That means for this problem, angle A is going to be equal to the inverse cosine of A squared, and A is 11. So 11 squared minus B squared, which is 5 squared, minus C squared, which we found to be 6.53 squared, all divided by -2 times 5 times 6.53, which again was side length C that we found earlier.
Put that on a calculator.
And we can put that in a calculator. There are no more variables left there, which means it's something I can put in a calculator and find. Again, make sure your calculator is in degrees because we're solving for degrees here, not radians. Okay, what'd you get when you threw that into a calculator? 144 point, we're going to round that up to 80 because it should round up 2 decimals. Okay, awesome. We have found side length C. We have found angle A. Sometimes it's helpful to write these values into your triangle as you're finding them. So we found that this is 144.80 degrees and that side length C is 6.52. What's the only thing left to find?
6.53.
Oh, it sure is a 3 and I just wrote a 2.
Do we just
Bloop.
subtract 180 from 144?
Yeah, we could technically use the derived version for angle B because we know all the side lengths and do the same thing we did in this like second part here with the purple formula. Or we can remember that angle B is going to be equal to 180 degrees minus angle A minus angle C, because that fact has not changed for triangles. They're no longer right triangles, but that fact still exists, which means that we very quickly can figure out that angle B should be equal to 15.20 degrees. And we have solved the triangle. This was a lot easier when it was a right triangle because one of the angles we already knew. So we were able to do easier trig, and so SOHCAHTOA worked. But when it's not a right triangle, we don't have those same things. We don't have a hypotenuse. So we're going to have to use other laws of triangles, including the law of cosines. Okay, major questions before we keep going for this. Ready, set, go. Okay, let's go to the next one. We're still going to do the same thing where we're going to solve the whole triangle, but we're going to be given different stuff this time. So let's start by just drawing the triangle first. It's going to be drawn in the usual way, which means, again, try not to make it look like a right triangle. Whatever your triangle looks like is fine. You have angle A, opposite of that is side length A. You have angle B, opposite of that is side length B. You have angle C, capital, and then a lowercase c across from it. We fill in what we know. What did they give us on this problem?
ABC.
A, B, C. They gave us all of the sides. That means this is a side, side, side problem, which again is one of the ones we're going to be able to use the law of cosines for. So the first one we did was side, angle, side. This one is going to be side, side, side. That's a weird looking 9. Let me fix that. Okay, so we're going to play the game of what do we find first. We want to use the law of cosines, because that's what this notes is called. For the law of cosines, we need to find an angle measurement.
Let's find C.
Let's find C? Okay. If we find side length C, which of the law of cosines formulas am I going to use?
The first one is the
The inverse.
We're going to use an inverse one, but what should it be solved for?
C squared.
So the version of it we're using is going to be the c squared equal to a squared plus b squared minus 2ab cosine of angle C. That's the one we're using, but we want to use the derived version of it. So either derive it again for angle C or look at the pattern for the one we solved before this. The one that we solved before this, and I put the little clouds around, had the angle equal to the inverse cosine of, giant fraction, the same letter squared minus the other two letters, both squared, divided by -2 and then the other two letters. So we can still derive the formula and continue using that pattern to get a formula that we want to use. We are trying to find angle C, but we know side length C, we know side length A, we know side length B. Again, we know side length A and we know side length B. So this is going to be good. We can plug all the stuff in. Angle C is going to be equal to the inverse cosine of 5 squared minus 9 squared minus 7 squared divided by -2 times 9 times 7. Is anybody confused where I got the 5, 9, and 7 from?
Just to be clear, the original equation with the cosine and punctuation, that's a capital C, right?
Yes, so these right here are always going to be angles, so they should always be capital letters.
Okay.
Yeah, inside the cosine is always a capital letter.
And then so you repeat the same thing with the same equation. Just switch them.
Essentially, yeah. So if we find angle C, what did you get for angle C?
33.55 or 60.
I'm looking at the wrong example. 33.5 what? 56 degrees. Okay, cool. So we round to 2 decimals. We call it a day. So now we have one more angle. We need to find another angle. Which one would y'all like to find? B. Okay, we're going to use the same idea, the derived formula for B. Let's see if we can get the pattern right. Angle B is going to be equal to the inverse cosine of what letter goes first? B squared, so same letter, yes, minus B squared, I put the wrong C squared, yeah. So the other two letters, divided by -2 times which two letters?
A and C.
A times C. Cool, we have the derived formula already for B. It follows the same pattern. We still know all of the side lengths, A, B, and C, so we have everything we need to plug in. Angle B should be equal to the inverse cosine of 7 squared minus 9 squared minus 5 squared, all divided by -2 times 9 times 5. And again, that's something I can throw into my calculator to find this angle. So when you plug it in, you'd get 50.70 degrees. All right, we're almost done solving the triangle. What's left to find? Angle A. Now there are two ways you could do this. We could either do this the easy way or the hard way. Which way would you like?
Easy way.
Easy way. If we know it's the easy way, triangles' degrees should always add up to what? 180. And if I already know two of the angles, then to find the last angle, all I need to do is subtract those angles from 180 degrees. So 180 degrees minus angle B minus angle C should give me angle A. And it should be what? 95.74 degrees. Now, yes, you totally could have used the derived version for A. With the side lengths, you'd get the same value. That's just more work. So once you have two angles, you always have the third. Once you have two angles, you always have the third. Okay, questions about the second one? This is for side, side, side. So when you have examples on your homework that are Side angle side, you're going to look at this example. And when you have examples on your homework that are side, 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 you're going to look at this example. Yes. Once we discover the law of cosines, though, it actually opens up, again, because it's generalized Pythagorean theorem, it actually opens up a lot of other formulas for things about triangles that we weren't able to do for triangles that weren't 90-degree angles until now. So if we look at the angle formulas, area formulas that are here, if you combine the idea of triangle area, 1/2 base times height, and the law of cosines, I'm not going to derive the formula for it, I'm just going to give you the formula. You can generalize the formula for a triangle for any side, angle, side triangle. Because if you know two sides and the angle in between them, you have everything you need for these formulas. They are, and again, the pattern kind of repeats itself. The area of the triangle is 1/2 side length B times side length C times angle A, or the sine of angle A. This follows from the law of cosines, but again, I don't think you care about the proof. Or it can be 1/2 angle A, or side length A times side length C times the sine of angle B. That's side angle side. And again, for the other one, if you know these three things, A, B, and side or angle C, you have a different formula for that one. So it gives us new formulas for area where we don't need to know the altitude or the height of the triangle. We would just need to know that angle in between things, which is kind of cool because then we don't have to find right angles. So here's where that might come into handy, a kind of cool problem that uses it. It says find the area of a regular octagon inscribed inside of a circle with a radius of 9 inches. Okay, first of all, how many sides does an octagon have? 8 sides. It being regular just means that all of the sides are the same length. So if we were to draw an octagon inside the circle, that's what inscribed means, here's what it might look like. And it's going to take me a while to draw this because octagons are not the easiest shape for me personally to draw. Octagon is like the stop sign. And we're going to pretend like all of those side lengths are the same. There's my octagon. It is inscribed inside the circle, which means all of the vertices of the octagon are on the circumference of the circle. Cool. We want to figure out this entire area. So not the circle itself, but the octagon inside of it. Okay. Here's how we might try to tackle this problem. The only other piece of information we were given is that the radius of this circle, so from the center to the circle's edge, is how many centimeters? Or sorry, inches. 9 inches. So if that is a radius, isn't this also a radius? So I have found right now, let me write that differently so it's not sideways. 9 inches. I have found a side and a side. To use the formula, I need it to be side angle side, which means I want to figure out what this angle is right here. How could we do that? Yes, okay, so we know an entire circle would be 360 degrees. And if we have these little slices here, there would be how many slices around the whole thing? 8. So if we wanted to figure out that theta, we'd know that the theta is just going to be equal to 360 degrees divided by my 8 slices, which is 45 degrees. So I know that this is 45 degrees. My formulas are side, angle, side. All 3 formulas that are up there in that little box for the triangle area and law of cosines are all sides, angles, and sides, which means if we wanted to find the area of just a little slice of this, so area of a slice is going to be 1/2 the radius, which is 9, times another radius, those are the 2 sides, times the sine of 45 degrees. That's the theta in between them. That's exactly what those formulas tell me. No, I don't have them labeled A, B, and C, but I totally could. This is angle A. This is side length A. This is angle B. This is side length B. This is angle C. This is side length C. we had a formula, the one that used angle A, that also used side lengths B and C. So this is the correct formula. Well, that's something I can throw into a calculator. This is also something you can do in your head. So if it were on the non-calculator portion of the test that you're going to take next week, what I would do is 1/2 times 9, that's 81 divided by 2. Sine of 45 is something you should have memorized. What's the sine of 45 degrees? Square root of 2 over 2, which means this is really 81 times the square root of 2 over 4. Oh, look at those fraction rules we practiced earlier. Top times top, bottom times bottom. That would be what is called an exact answer, if I had asked you for an exact answer. But most likely, I'm going to ask you for an approximation, which means you can throw that into a calculator. 81 square root 2 divided by 4, 28.64 inches squared. Of course, again, so this is an exact answer. This is an approximate answer. So if it's on the non-calculator portion, obviously you can't take the square root of 2 in your head. I don't think you have that memorized. And then approximate would be the one you put in a calculator. But that's just the area of the slice. What was the question asking you? Of everything. So instead of just taking the area of a slice, if I want an area of the octagon, what am I going to do with the area of the slice? Multiply it times 8. So if we take 8 times the area of the slice, that's going to be 8 times 81 square root 2 over 4, which the 8 and the 4 are going to reduce to 2 over 1. 2 times 81 is 162 square root of 2. There's your exact answer. But if it's on the calculator portion of the test, you would just throw that into a calculator or throw the original approximated answer into a calculator and multiply it by 8. That'd be 229.10 square inches. So if you ever want to overanalyze the kind of octagon you can put on top of a pizza, now you know how you can. Another formula that comes from the law of cosines and allows us now to do more things is called Heron's formula. In Heron's formula, this is going to be especially helpful when you have the 3 side lengths of a triangle. So the one above this was area when you had side, angle, side. This one is area when you have side, side, side. This formula says that if we let S denote what's called the semi-perimeter, which semi means half, like semester is half of a year, so semi-perimeter is half of a perimeter, and perimeter is adding up all the sides. So, oh, look at the formula. You added up all the sides divided by 2. That's a semi-perimeter, half of the perimeter. Then the area of the triangle is given by the following formula. The square root of the semi-perimeter times the semi-perimeter minus A times the semi-perimeter minus B times the semi-perimeter minus C. So if we wanted to answer the question number 4, and it says find the area of the triangle with these 3 side lengths, I don't have any angles to work with, so I'm not going to use the formulas from the top of the page. I'm going to use the formulas from Heron's formula, which means I first need to figure out what my semi-perimeter is. Semi-perimeter is just the 3 side lengths added together, so 13 plus 15 plus 18, and divided by 2. 13 plus 15 plus 18, all divided by 2, is 23. So my semi-perimeter is 23. Once I have the semi-perimeter, I also already have A, B, and C, or what we're going to label A, B, and C. So I have everything I need to plug into this formula. The area of this triangle is going to be equal to the square root of 23 times 23 minus 13 times 23 minus 15 times 23, I'm running out of room, minus 18. I've just filled in the formula. Do we see that? Filling in the formula? Okay, great. You could take this piece by piece. If it was on a non-calculator portion of a test, you would do 23 times 10 times 8 times 5. You'd multiply all of those things in your head. You'd get 9,200, and then you would need to actually take the square root of that. An approximate answer where when I do the like little tree and I factor out all of the pairs, okay, I square root all the pairs of numbers, it'd be 20 square root of 23. But if it's on the calculator portion, I'm most likely going to ask you for an approximate answer or a rounded answer. It'd be 95.92 units squared. They didn't tell us what we're measuring in, so we call it units squared. So if it's on a calculator portion, you go from here to here. Just throw it in a calculator.
Is this just another way of finding the area of a triangle?
Yes.
Okay.
Because before today, the only time we could find the area of a triangle was 1/2 base times height. That was what's the word I'm trying to, assuming that your height is a 90-degree angle. We don't have 90-degree angles anymore, so we can't assume that. So these two formulas allow us to do the area of these triangles that don't have altitudes or 90-degree angles. So there's no height to them. Here's another cool application of the law of cosines. It says the bases on a baseball diamond are 90 feet apart, and the front edge of the pitcher's rubber is 60.5 feet from the back corner of home plate. Find the distance from the center of the front edge of the pitcher's rubber to the far corner of first base. So my people who do not play baseball or softball, here's what it looks like. They're telling us that the distance from this where the batter stands, home plate, to the pitcher is 60.5. We want to, and then if you didn't know, which I didn't know until, because I didn't play the sport, the distance between the bases for baseball is 90 feet. So that was a fact that we had to know that I didn't. Also that this is a 45-degree angle. Those are just facts about a baseball diamond. What we want to figure out is the distance from the pitcher's rubber to the back edge or side edge of first base. So we want to figure out what side length of this triangle. C. We want to find side length C, so let's figure out what we know. What measurements do we have?
90 feet.
Not necessarily 90 degrees here. It's drawn like it looks like it, but it's not because it's actually tilted up a little bit. We have angle C though. What is angle C? 45 degrees. What else do we have?
Side length B.
We have side length B, because remember B is across from angle B. What else do we have?
Side length A.
Side length A, because it's across from angle A. What formula have we been using today that would use, or find me side length C using side length A, angle C, side length B?
I don't know that any but the third one of the three.
Yeah, the third one of those three. That's the law of cosines solved for C. And since that's a whole page away, we'll write it down again. That's C squared. Sorry, that should be a lowercase c. I gave it a little too much. Side length C equal to, I'm hearing you murmur it to yourself. That's the one from the other page. We want side length C. So the other two sides are A and B. That's what's in the formulas. And the angle across from side length C is capital C. Well, we know all those things, so we just have to plug it in. That's going to be 60.5 squared plus 90 squared minus 2 times 60.5 times 90 times the cosine of 45 degrees. I'm not going to make you do that one in your head, even though cosine of 45 degrees we should know. When we throw that into a calculator, what do you get? 4,059 point what? 0.86 feet. But that is C squared. Also, hopefully you're like whoa, they are not 4,000 feet apart on a baseball field. Hopefully they're like, something was wrong with that answer. Because that's c squared. What is c, though? 63.72 feet. So on a baseball field, that's how far apart the pitcher's rubber is to first base.
So this is just
Took the square root.
this is just assuming that the pitch isn't like straight, right?
Like it's not a 90-degree angle.
It's not a 90, yeah, okay.
No.
Because I was gonna ask, why can't we just not use just sine?
The first base is slightly behind the pitcher's rubber, so it's not a 90-degree angle.
Oh.
It doesn't look like it in the drawing on here, but in reality it's behind, so it's not directly flat, so it's not a 90-degree angle. It's like tilted up a little bit. Yeah. Huh? What? The law of sines, which is a new law, states that the ratio of the sine of an angle to the length of the opposite side is the same for all three laws of any triangle. It is actually an extension of congruence for Euclidean geometry. Now, you know this, you may not know it was called Euclidean geometry, but you actually know a bunch of congruence laws from when you took geometry. We've already talked about two of them. We can prove congruence of triangles if they have sides, angles, and sides that are similar. We can do it for side, 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 which were the two we used for law of cosines. Does anyone remember any other congruence theorems that we could have?
There's 2 letters, but I forgot.
They're all three letters, but they're all either A or S in different combinations.
S S A. No, wait, no, side, angle, side, 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 side. Angle, angle, side.
Angle, angle, side is one of them. Okay. Angle, side, side, which I'm going to write as side, side, angle, actually is one of the no-nos. I'm not going to write it the other way. Okay. It's one of the ones that does not prove congruence. And actually, for this lesson, you actually can use law of sines for it, but we're not going to this year because of the snow days. We're going to leave that example alone because it's a monster. The other one that's a no-no is angle, angle, angle. You can't prove congruence with that because you have no idea what the side lengths are. If the angles are the same, it could just be all sorts of expanded. There's one more we're forgetting.
Angle, angle, side. Angle, side.
Angle, side, angle. So these two triangles are going to help you when you have the law of sines. So those are the ones we're going to be working with today. And like I said, the third one that we have in the non-congruence, side, side, angle, technically you can use law of sines for, but we're not going to this year just because of time and the snow.
Wait, yeah.
Okay, so the law of sines is a bunch of ratios, which means we're going to do a bunch of proportions today. This is another something that I'm going to have you memorize. I will not be giving you the law of sines. I expect you to memorize it, but it's actually really pretty simple because what do you notice about those three ratios, the three fractions? They're all sines. What else? They match letters. So sine of angle A is over side length A. Sine of angle B is over side length B. And sine of angle C is over side length. That should be a lowercase c. My bad. Lowercase. Oops. Sorry, that's a lowercase c. I would have noticed if these letters looked different. So you know you want to use the law of sines when you know an angle and its opposite side. So if you know both of those things, which we didn't in the last examples, we were always had one but not the other. If you have an angle and its opposite, you're going to want to use law of sines because it's way simpler to do a proportion than derive a formula and use an inverse cosine. Okay, so we're going to do the same sort of question as before. It's going to give us information about a triangle, and we want to solve for what we don't know. So let's draw it first. I would use your small handwriting. I don't think I left you enough space to write big. Okay, so here's my triangle. Oof, not great. It'll do. We have angle A and side length A, angle B, side length B, angle C, side length C. We label what we know. We have angle A is 36 degrees. Angle B is 48 degrees. And side length A is 8. Knowing that I just wrote two things down in the same color is a huge indicator that we're going to be using law of sines because we know the ratio for both big A and little a. So if we wanted to find the missing stuff, we set up some proportions. Okay, this is angle, side, yes. So if we set up our first proportion, I'm always going to make sure my proportion is using sign of capital A over lowercase a, because I know both of those things. Now the proportion that I set it equal to, I need to know something about. What other thing do we know? Angle for which one? B. So I want to use angle B, which means the lowercase letter I'm going to use is also B. Of those four letters, which one do I not know? Of these four letters. Lowercase b, but that's only one thing I don't know. One equation, one unknown I can solve. So here's what it's going to look like. We're going to have the sine of 36 degrees over 8 equal to the sine of 48 degrees over b. That's a proportion. What do we do to solve proportions? If we proportion them, no.
Is it the
Cross multiply.
Cross multiply and divide, butterfly method, whatever you called it, that's what we're doing here. So we cross multiply, it's going to be 8 times the sine of 48 degrees equal to b times the sine of 36 degrees. So that's cross multiply. And then what? I subtract?
No, you
Divide.
divide.
Okay, so eventually it's going to be b is equal to 8 sine of 48 degrees divided by sine of 36 degrees. Well, that stuff I can throw in a calculator. We cross multiply and divide. That's butterfly method from way back when. It should be 12, maybe? Is it 11?
yeah.
Okay, fabulous. And what are we measuring in here? It doesn't tell us, so we're going to put units behind it. So that's how long side length B is. Cool. Now that we know side length B, we have all of A's, and now we have all the B's. What's left to find?
C's.
Okay, don't think too hard. How can we find angle C?
B subtracted from 180.
Yeah, subtract it from 180. Because we know two of the angle measurements, correct? We can very easily find C by remembering, again, the old geometry thing, that C should be equal to 180 degrees minus angle A minus angle B. Which is, C would be equal to 96 degrees.
Why didn't we find this first?
That's a great question. We could have done it first.
Oh.
But now we need to find little c. Very good. Because now that we know angle C, we know that this is 96 degrees. Again, I sometimes find it helpful to draw it in. We still know the ratio for the A's, but now we want to find little c. It's going to look exactly like the problem we just did, except no longer B's, it's for C's. I'm going to leave y'all to do this for a second. See if you can find me side length C. That's actually a really good question. Did y'all hear her question? It doesn't matter. After you have found this ratio in B, if you had compared it to B, I only avoid doing that because I know I rounded this number. And so if we're really trying to be the most accurate we could, we wouldn't want to use a rounded number. We would want to continue to use the givens, which is big A and little a. But you should, especially because this is not as accurate, or like at this level, it's not going to change the accuracy. You should have gotten the same sort of thing.
Wait, 13.54?
13.54. It's off by like a smidgen, right?
Wait. What's the 3 decimals you got? Because I got 10.
Okay, I'm going to help you through one part of this next question, but then you all are going to figure out two more parts. For this one, which is going to be a side-side angle, when we draw it, here's what it might look like. That one kind of looks like a 90-degree angle, but it's not a 90-degree angle. Don't mark it as one. Okay. So we have angle A, we have side length B, and we have side length A. So automatically, I see that I have both an angle and its opposite. That's the indicator that I can use the proportions, law of sines, instead of law of cosines, which you could still technically use here. It would just be a harder thing to solve for. Okay, so when we set this up, what do y'all want to find first? What should we find first? There's actually a good answer to this one. Big B, because we know A's and A's, so that's going to be one of my proportions, and we know part of the B's. We know little b. So when we set up our proportion, which is going to be sine of angle A over little a, equal to sine of angle B over little b, I only fill in 3 of those numbers. I'm going to leave 1 as a variable. It'll be sine of 26.3 degrees over 7 equal to the sine of, I don't know b, so I'm going to leave it as a variable, over 6. We cross multiply and divide. So it's going to be 7 sine of b equal to 6 sine of 26.3 degrees. What do I divide by this time? 7. Because the b is contained within the sine function right now. I first have to isolate the sine function, then I can actually do something with the sine function. It's kind of like when you learned about absolute values in Algebra 2, you had to isolate the absolute values and then do something with them. Same idea. But what do we do with sines to get rid of a sine? Arc sine, the inverse sine. Very good. So really, if we take the inverse sine of both sides, or the arc sine of both sides, you should be able to find b. Now that's something I can throw in a calculator.
Question, would we ever use cosecant and secant stuff again?
So technically when we were doing the real world problems, anytime you had to divide, but like 12 divide by tangent, you could have done 12 times cotangent since that's the reciprocal. So yes and no. You can choose to use them or you can choose not to. But for law and sines and cosines, no, it only uses sine and cosine. Okay, here's where I'm going to leave you. I want you to finish this one and then finish finding me angle C and side length C.
Oh God.
You got it. Don't look up here until you're ready. I'm going to start writing it down, what I did, at least. Yes.
We're at 3, so it's great. You put a 5 for 26.3.
Whoop. Thank you. Embarrassing. Okay, I know I'm cutting off some of your thinking. Were we on the right track at least? We just needed more time. Okay. So don't forget the part B of this, which was finding angle C, was the easy part. If you know two angles, you know the third. 180 minus the other two angles. And then we could set up law of sines again. Again, yes, you could use law of cosines there as well if you find that easier. Up to you, pick your poison. I personally find law of sines easier. So I'm going to use it at all costs because proportions are easy for me. Okay, we're kind of going to jump around here a little bit just because of time. Additionally, this next example on this page is the example we were going to skip anyways. This is what was called the ambiguous case, which basically means the triangle could be made two ways, so we had to solve it twice. We're not going to worry about that. You won't be asked questions about that. Moving on. What we're going to do is problem number 4. If you're interested in number 5, that will be on the notes online, but we're not going to solve it here. We're just going to do the application for law of sines here. It says, Forest Ranger Chris Johnson is at Ranger Station A. He sights a fire in a direction 32 degrees east of north. Okay, first of all, what? Here's the Ranger Station A. And if we are measuring this east of north, first of all, never eat soggy waffles. Do we know that? Never eat soggy waffles.
Never ever stop women.
That also, but also never eat soggy waffles is a thing that we used to say. I just know it. That's fine too. So east of north means that he's sighting the fire 32 degrees east of north. Here's going to be my fire. Please don't laugh. Okay, there's the fire.
That's pretty hot.
Thank you. And then we keep reading, and a question continues to say, Ranger Rick Thorpe is at Ranger Station B, 10 miles due east of A. So here's B. So this is 10 miles east. It sights the same fire on a line 48 degrees west of north. Oh, pretend like that's a straight line, please. That's embarrassing. Here's what we have. It says, find the distance from each ranger station to the fire. So the distances we're trying to find is the distance from A to the fire, which is side length what? B. And we want to know the distance from Ranger B to the fire, which is side length what? A. We got to figure out what we know, though, because all we were given were these degrees from north. What is angle A, actually? That's right here. What would be angle A? What kind of angle is made when you look north and east? Oh, north and east make a 90-degree angle. So how much is theta? 58 degrees. Okay, so we already know that one. Whoa, what numbers did I just try to write? 58 degrees. Okay, what about B? The same thing, but not that. 42 degrees, because again, it makes a right angle. West and north make a 90-degree angle. So what else do I know?
You know the area of the triangle, or like the inside angle. That one.
That one. Angle C. What is angle C? 80. How did you figure that out?
180 minus 58 minus
180 minus A minus B gives me C. Cool. Okay, so all I've done so far is this. If we're trying to find side length B and side length A, what ratio do I already know that I could use to find them?
A and B.
Ooh, I don't know B yet. What do I know, though?
A and C.
Yes.
C and C. So it should be the same letter. I know C and C, right?
Yeah.
Which means I'm going to help find these different things, I'm going to use C and C as my ratios. Angle C over side length C equal to, we'll do the Ranger Johnson first. So that's side length B. So we want to do sine of big B over little b. And for time, we'll only find this because it's just a repeat of the steps. So we're just finding the one for Chris Johnson here. Fill in what we know. This is the sine of 80 degrees over 10 miles equal to the sine of 42 degrees over b miles. Oh, look, it's an easy proportion we can solve. 10 times the sine of 42 degrees equal to b times the sine of 80 degrees. Divide by sine of 80 degrees. We would get that the distance that Chris Johnson is at Ranger Station A to the fire is 6.79 miles. And for time, we'll stop there, but Ranger Thorpe, which is side length A, literally the same sort of thing. You set up your proportion using C over C's, and you can solve.
So like, what if there was like actually a fire, and then Ranger Johnson stopped and was like, all right, how far am I from this fire?